This video is for Math 116, and this is section 1.5, what we call toolbox functions. So it's about all the different types of standard functions that we can talk about in mathematics. So from a mathematical standpoint, it's good to familiarize yourself with the different types of functions that mathematicians work with. From an applied standpoint, as I addressed in the textbook, this is helpful in statistics. I once had a friend who was an MD, and he wanted to do some testing. He was measuring something in the blood, and then he would prescribe some medicine, and then the patient would come back and he would take a second measurement, and he wanted to compare, and so then he was graphing those two measurements on an X and Y axis, and he wanted to know how to analyze and interpret that information. And so part of what happens when you're getting statistical data, is that it can take different shapes. I guess that's more of a linear scenario. This is more of a quadratic relationship. And you also, well, actually one thing that happens frequently is you get what are called these logistic relationships, which we talk about a little bit in Math 111 and then again in calculus. These logistic relationships are very interesting. They're very applicable to a lot of different scenarios, including the COVID pandemic. It's sort of a modified exponential function. So before I leave off on that, let me just mention to you a little bit about what a logistic function does. We won't talk about it a whole lot in this class, but it is really applicable, and it's been on my mind recently because of the COVID epidemic. So here's a standard exponential graph. The fact is, most growth is restricted in some way. Okay, whether it's population, whether it's physical growth, most things tend not to grow like this, okay, because their growth depends on resources, and as those resources are consumed, that puts pressure on the growth, okay? And so a mathematician somewhere in the 1830s, French mathematician came out with he started with the same idea as an exponential growth, but then he introduced a factor that caused that growth to be limited when the resources were limited, and that created what's called the logistic function. And so the beginning of it looks a lot like an exponential growth curve, but then at this inflection point right here, that's the point where the resource scarcity starts to kick in, and then the growth is diminished. And if you look at population in places where the geography is limited, places like Rhode Island, Manhattan Island in New York City, England itself, their population graphs tend to follow this generalized shape. You get this period of exponential growth, but that growth puts, like I keep saying, restrictions on the resources, and that causes the growth to slow down, unlike the exponential. Okay, so in section 1.5, we've got some examples of the standard types of functions. You've got the constant function, the linear function, absolute value, the rational function, quadratics and square roots, and cubic and cube roots. And then at the bottom there, I put a couple of typical functions that we won't cover in this section, and those are exponential, logarithmic, and of course the logistic, as well as trigonometric functions, which we save for the Math 112 course. Okay, so the exercises on pages 36 and 37, problems 9 through 20 are matching problems, so I'm not going to do any of those. I'm going to leave it for you to match those up with the pictures on page 37, but I will take a look at the problems 2, 4, 6, and 8. Okay, so let's see here. Problem 2, we want to sketch a graph where f of x is x squared minus 4. And these don't have to be too exact. If you have a grid to graph on, it is good to make sure that your graph is passing through some realistic grid points. But if we're just going to do a little sketch of this, we know the standard graph of y equals x squared is going to look something like this. Okay, so then y equals x squared minus 4. That vertex, the vertex is going to move down to 0, negative 4. And there we go. Y equals x squared minus 4. And that just gives us a general idea for what that graph is going to look like. Let's see here. Problem 4. We've got f of x is going to be x plus 1 all squared minus 4. Okay, so similar process, except this time the plus 1 inside the parentheses is going to shift the parabola 1 unit to the left and then down 4 units. And so that's going to put the vertex here at negative 1, negative 4. And let's see here. I was just debating about where that y intercept was going to be. And this should be negative 3, right? Because this is going to be x squared plus 2x plus 1 minus 4 up to x minus 3. And so if x is 0, then your y coordinate, right here, will be 3. Okay. All right. So that's some pretty straightforward, simple transformations on the parabola. The absolute value graph, so if you think about this, y equals absolute value x, you're taking the line y equals x and you're reflecting all these negative y values over the x-axis to make them positive. So there's our standard absolute value graph, is going to look like that. Let's see here. So number 6, we want to graph f of x is absolute value x plus 5. So all that's going to do is push it up 5 places. And that, I don't know if we would call it a vertex or not, but that's going to be at the point 0, 5. And there we go. There's a good sketch for that one. And then the next one, problem 8. F of x equals absolute value x minus 1 plus 5. Yeah. Okay. So this is going to shift 1 place to the right and then up 5. And so that graph will look something like this. And this point is going to be at 1, 5. Okay. All right, so that's pretty much it for this section. Like I said, I'm going to leave that matching section for you all to do, because if I just pick out a couple of the problems in a matching section, it kind of ruins how those things are supposed to work. So let's see, I think that's it for transformations in this. The next couple of sections, we'll talk about composition of functions and inverse functions and a couple other things before we get to the end of the chapter, where we take a look at those applied maximum and minimum problems. So, as always, if you have any questions, please let me know. Thanks.